Imagine the fabric of space itself stretching and compressing like the surface of a pond disturbed by a falling stone, only this ripple isn't made by anything so small. Picture two black holes, each weighing billions of times more than our Sun, locked in a death spiral, orbiting closer and closer until, in a fraction of a second, they collide with a force so violent it warps the very universe around them. These aren't just abstract ideas, they're real events happening right now in the distant cosmos, sending gravitational waves racing across space at the speed of light. And here's the astonishing part, we can detect them. For over a century, Einstein's theory of relativity predicted these ripples in spacetime, but it wasn't until 2015 that humanity finally caught its first glimpse. The discovery was like hearing the universe whisper its deepest secrets for the very first time. Gravitational waves aren't just cosmic curiosities, they're messengers, carrying stories of the most extreme events in existence. Neutron stars tearing each other apart, supermassive black holes merging in darkness, and perhaps even echoes of the Big Bang itself. Every ripple holds clues about how the universe works on scales so vast, so violent, they defy imagination. In this video, we're diving into 30 mind-blowing facts about these gravitational waves, from how they're detected by laser beams traveling down tunnels miles long, to what they reveal about the invisible skeletons of reality, black holes and wormholes lurking in the cosmic shadows. You'll learn how these waves could one day help us unravel mysteries like dark matter, extra dimensions, and whether time itself has a beginning. This isn't just science, it's a front-row seat to the most dramatic events in the cosmos, playing out in a language of spacetime itself. So buckle up, we're about to journey into the heart of some of the universe's most extreme phenomena, where the ordinary rules of physics break down and the extraordinary becomes routine. Einstein's genius didn't just reshape our understanding of gravity, it gave us a whole new way to listen to the universe. Back in 1916, his theory of general relativity revealed something astonishing. Massive objects like stars and black holes don't just bend space and time. They can send ripples through it like tossing a pebble into a still pond. These ripples, gravitational waves, were his prediction, but even Einstein himself doubted we'd ever detect them. The math said they'd be vanishingly weak by the time they reached us, lost in the background noise of the cosmos. For decades, many scientists dismissed the idea as pure theory, something too faint, too elusive to ever catch. But here's where the story gets thrilling. Proving Einstein right required more than just brilliance. It demanded technology that didn't even exist in his lifetime. Imagine trying to measure a distortion in spacetime smaller than 1/10,000th the width of a proton. That's like detecting a single grain of sand on a beach from light years away. Early efforts in the 1960s and 70s ended in frustration, with detectors too crude to pick up anything. Then came breakthroughs like lasers and vacuum chambers precise enough to isolate vibrations from passing gravitational waves, the real game changer. LIGO, the Laser Interferometer Gravitational Wave Observatory, a pair of colossal L-shaped tunnels stretching 2.5 miles long, built to sense the faintest tremors in the fabric of reality. And then, on September 14, 2015, after a century of searching, LIGO caught its first wave. The signal came from two black holes, each about 30 times the mass of our Sun, colliding over 1 billion light-years away. In less than a second, they merged with a force so intense it briefly outshone every star in the observable universe combined. The ripple they sent out was tiny by the time it reached Earth, just a fleeting wobble in the lasers, but it was enough. After all those years of doubt, Einstein's prediction was confirmed in the most spectacular way possible. This wasn't just a victory for physics, it was humanity tuning into a cosmic symphony we never knew existed. That first detection in 2015 wasn't just a triumph. It rewrote the rules of astronomy forever. Scientists called the signal GW150914, but its significance was anything but dry or technical. Imagine the moment when the LIGO team saw that distinctive chirp in their data, a split-second wobble in their lasers, so faint it could have been mistaken for a glitch. But this was no error. The pattern matched Einstein's equations perfectly, the telltale spiral of two black holes, each dozens of times heavier than our Sun, whipping around each other hundreds of times per second before merging in a cataclysmic crash. The energy released was staggering. For a brief instant, it outpaced the combined light of every star in the observable universe. All of that violence compressed into a gravitational wave that traveled 1.3 billion years just to reach us, stretching and squeezing Earth by a fraction of an atomic width as it passed by. What made this discovery so revolutionary wasn't just proving Einstein right, though that alone would have been monumental. It was the birth of an entirely new way to explore the cosmos. Before LIGO, astronomers relied on light-visible, X-rays, radio waves to study the universe, but gravitational waves, they're immune to the dust and gas that obscure telescopes. They barrel straight through matter, carrying undistorted tales of events too dark or distant to see. Suddenly, we had a backstage pass to phenomena hidden from conventional astronomy. Black holes colliding in the void, neutron stars tearing each other apart, even echoes from the universe's earliest moments. The impact was immediate. Just 2 years later, the Nobel Prize in Physics went to the pioneers behind LIGO, cementing gravitational wave astronomy as one of humanity's greatest scientific achievements. But the real excitement lay in what came next. That first detection was like hearing the opening note of a symphony, a hint at the cosmic orchestra waiting to be discovered. Since then, LIGO and its counterparts have detected dozens more waves, each revealing new extremes. Black holes far heavier than theory predicted, neutron-star collisions spraying gold and platinum across space, even mysterious mergers that defy classification. Every ripple is a puzzle piece, helping us assemble a deeper, richer picture of how the universe operates in its most violent corners, no longer just observing the cosmos, but truly listening to it. Gravitational waves don't just carry secrets from the universe's most violent events, they deliver them at the ultimate cosmic speed limit, the speed of light. That's right, these ripples in spacetime race through the cosmos at roughly 186,000 miles per second, the same blistering pace as a beam of sunlight. But here's what makes that speed so revolutionary. Unlike light, which can get absorbed, scattered, or blocked by cosmic dust and gas, gravitational waves slip through everything completely undisturbed. Imagine shouting into a storm. Your voice might get drowned out by wind and rain, but a gravitational wave is like a perfect, crystal-clear whisper cutting straight through the chaos. This unimpeded journey means gravitational waves give us a pristine snapshot of their origins, free from the distortions that plague traditional astronomy. Take colliding black holes, for example. If one of these catastrophic mergers happened behind a thick nebula, telescopes would see nothing. No X-rays, no gamma rays, just darkness. But gravitational waves, they pass right through, carrying every detail of the collision as if nothing stood in their way. It's like having a front row seat to events that would otherwise be hidden behind a cosmic curtain. Compare that to electromagnetic waves, the light and radio signals astronomers have relied on for centuries. Those signals can be bent by gravity, absorbed by dust, or even smeared by interstellar plasma. By the time they reach us, their stories are often fragmented or obscured. Gravitational waves don't just offer an alternative, they provide a clarity that's almost poetic. When LIGO detected the collision of two neutron stars in 2017, telescopes also spotted the accompanying flash of light, but it arrived slightly later, delayed by its struggle through interstellar material. The gravitational waves, though, They showed up right on time, pristine and untouched, like a messenger arriving with urgent news before the rest of the world even knew something had happened. This speed and transparency opened doors to discoveries we couldn't even dream of before. Imagine detecting the moment two supermassive black holes merge at the dawn of time, their waves traveling unimpeded for billions of years to tell us about the universe's infancy. Or catching signals from exotic objects we've never seen: primordial black holes, cosmic strings, even defects in spacetime itself. With gravitational waves, we're not just observing the universe anymore. We're tuning into its purest, most unfiltered signals, hearing the cosmos speak in a language that light could never translate. If the universe has a soundtrack, gravitational waves are its bass notes, deep, resonant, and born from the most extreme collisions imaginable. These ripples in spacetime don't come from gentle events. They're forged in cosmic furnaces where gravity twists reality to its breaking point. Take black hole mergers, for instance. Picture two monsters, each with gravity so strong not even light can escape, locked in a death spiral. As they orbit faster and faster, they churn spacetime like a blender, sending out waves that surge across the cosmos like a tsunami. When they finally collide, the energy released is beyond comprehension. In that split second, they can outshine every star in the observable universe combined, not with light but with raw gravitational force. But black holes aren't the only players. Neutron-star collisions are just as spectacular. Imagine two city-sized objects, each so dense a single teaspoon of their material would weigh 1 billion tons, smashing together at nearly the speed of light. The impact doesn't just send gravitational waves rippling outward, it also sparks a fireworks show of gamma rays and scatters heavy elements like gold and platinum across space. In fact, the gold in your jewelry might have been forged in one of these violent mergers billions of years ago. Then there are supernovae, the explosions of massive stars. When a star many times heavier than our Sun runs out of fuel, its core collapses in a heartbeat, unleashing a shockwave so powerful it can briefly outshine an entire galaxy. If the collapse isn't perfectly symmetrical, it can send gravitational waves pulsing outward, a last cry from a dying star, and the grandest source of all. The Big Bang itself. Theorists believe the universe's birth was so turbulent it may have sent gravitational waves echoing through the fabric of spacetime, a primordial echo we might one day detect. These waves could carry secrets about the universe's first moments, back when all of existence was smaller than an atom. What ties these events together is sheer violence, gravity pushed to its limits, spacetime stretched and squeezed like taffy. Whether it's black holes merging in darkness or neutron stars colliding in a blaze of cosmic debris, gravitational waves are the universe's way of shouting its most dramatic stories across the void. And now, for the first time in history, we're here to listen. On August 17, 2017, the universe handed scientists a gift unlike any other, a collision so bright, so violent, it answered questions we'd been asking for decades. Gravitational wave detectors LIGO and Virgo picked up a signal labeled GW170817, a rhythmic chirp lasting nearly 100 seconds. But this wasn't just another black hole merger. For the first time, gravitational waves came with a visible counterpart, a brilliant flash of light across the electromagnetic spectrum. Telescopes around the world swiveled toward the source, capturing ultraviolet, infrared, X-rays, and gamma rays bursting from a galaxy 130 million light-years away. This was a kilonova, the explosive aftermath of two neutron stars smashing together at nearly light speed. The collision itself was almost unimaginable. Picture two city-sized objects, each so dense a teaspoon of their material would weigh as much as Mount Everest, locked in a fatal dance. As they spiraled closer, gravitational waves rippled outward like a siren's call. When they finally collided, the impact forged a fireball hotter than the core of a star, launching jets of material into space at nearly the speed of light. But the real magic happened in the aftermath. The explosion created a cloud of radioactive debris rich in heavy elements: gold, platinum, uranium, scattering them into the cosmos like cosmic seeds. This single event confirmed what theorists had long suspected. Neutron star collisions are the universe's ultimate gold factories. Before GW 170817, we didn't know where half the periodic table's heaviest elements came from. Now we had proof. The amount of gold produced in that one kilonova, roughly 200 times the mass of Earth, enough to coat every continent in a glittering layer. Suddenly, the jewelry on your fingers or the circuitry in your phone took on new meaning. These elements weren't just stardust, they were forged in the heart of a cataclysm so rare, so powerful, we'd never witnessed one until that day. Beyond the science, this detection marked a turning point in astronomy. For the first time, we didn't just see or hear the universe, we did both simultaneously. Multi-messenger astronomy, the practice of combining gravitational waves with light, had its first spectacular success. It was like watching a silent movie while suddenly hearing the soundtrack. The experience became richer, more complete. Telescopes saw the glow of radioactive debris, while LIGO waves revealed the precise moment the neutron stars merged. Together, they painted a full picture of an event that would have been impossible to understand with just one tool. The implications stretch far beyond a single explosion. Kilonovae like GW 170817 could help us measure the expansion rate of the universe with unprecedented precision. They might reveal new physics about extreme matter, conditions so intense even atoms collapse into a soup of quarks. And every new detection brings us closer to understanding how the universe builds the very elements that make planets, life, and even us possible. That flash of light in 2017 wasn't just a cosmic spectacle, it was a Rosetta Stone, decoding secrets written in the language of gravity and light. Black holes don't just collide, they rewrite the laws of physics in the process. When two of these cosmic monsters spiral toward each other, they reach speeds so dizzying they'd make a neutron star look sluggish. In the final moments before merger, they can whip around at half the speed of light, completing entire orbits in mere milliseconds. That's not just fast, it's a realm where classical physics starts to crumble. Newton's tidy equations about gravity, they can't even begin to describe this chaos. Only Einstein's theory of relativity, with its warped spacetime and time-bending effects, can capture the true madness of a black hole tango. The energy unleashed in these collisions is almost beyond comprehension. Picture converting the mass of 3 entire suns into pure gravitational waves in less time than it takes to blink. That's what happened during the first black hole merger. LIGO detected a burst of power so intense it briefly outshone every star, galaxy, and quasar in the observable universe combined. And yet, because black holes swallow all light, this cataclysm was utterly invisible. Only the ripples in spacetime betrayed its existence, like tremors from a silent earthquake. Then comes the ring down, a phase so bizarre it sounds like science fiction. After the black holes merge, the new, larger black hole doesn't just sit quietly. It vibrates, wobbling like a struck bell as it settles into its final form. These oscillations aren't random, they follow precise frequencies dictated by the black hole's mass and spin, creating a unique gravitational fingerprint. Scientists compare it to listening to a tuning fork ringing in the void. The pitch and decay of these waves reveal everything from the black hole's size to how fast it's spinning, clues we could never gather by light alone. What makes these mergers truly mind-bending is how they stretch our understanding of reality. The speeds involved warp time itself. Clocks near the colliding black holes would tick far slower than those on Earth. The gravitational forces are so extreme they create echoes of the merger, like space-time itself briefly rebounding from the shock and the ring-down phase. It's a direct window into what theorists call black hole hair, The idea that merged black holes retain only a few simple properties like mass and spin, shedding all other details in a cosmic reset. These aren't just cosmic spectacles, they're laboratories for testing physics at its limits. Every merger we detect sharpens our grasp of gravity's true nature, probing questions even Einstein couldn't answer. Could these violent events hint at hidden dimensions or cracks in relativity? Might the ring-down whispers contain traces of quantum effects near the event horizon? With each new detection, we're not just watching black holes collide, we're decoding the universe's most extreme physics firsthand. While the black hole mergers we've detected so far are spectacular, they're just the opening act compared to what's coming. Imagine a collision so massive it doesn't just ripple spacetime, it could warp the entire Milky Way. We're talking about supermassive black holes, the billion solar mass behemoths lurking at the centers of galaxies. When two of these giants eventually spiral together, their gravitational waves will be so powerful they'll distort the fabric of reality on scales we can barely comprehend. This future cosmic spectacle will require a whole new generation of detectors to observe. Enter LISA, the Laser Interferometer Space Antenna, set to launch in the 2030s. Unlike ground-based observatories like LIGO, LISA will consist of 3 spacecraft flying in formation 2.5 million kilometers apart, connected by laser beams. This floating triangle will detect gravitational waves at frequencies too low for Earth-based instruments, the deep, resonant hum of supermassive black holes merging across the universe. The scale of these events defies imagination. Picture 2 black holes, each weighing billions of times more than our Sun, circling each other for thousands of years before finally colliding. The gravitational waves they produce won't last mere seconds like the signals LIGO catches, they'll persist for years, like a never-ending earthquake shaking spacetime itself. The energy released would be enough to rearrange entire galactic neighborhoods, potentially altering the orbits of stars light years away. Here's the mind-blowing part. When these waves pass through our galaxy, they could briefly stretch and compress every object within it, including Earth, by detectable amounts. Your height might fluctuate by a fraction of a millimeter as the wave rolls through. LISA will catch these subtle distortions, giving us front-row seats to the most titanic collisions in the cosmos, events so powerful they could help us map the large-scale structure of the universe itself. These future detections won't just break records, they'll test Einstein's theory in regimes where it might finally break down. Some theorists speculate supermassive black hole mergers could create temporary time storms, regions where spacetime becomes so warped that clocks would run at radically different rates. Others wonder if we might spot hints of quantum gravity effects imprinted in the waves. Whatever secrets they hold, one thing's certain: when supermassive black holes collide, the entire universe will feel it, and for the first time we'll be listening. Gravitational waves don't just travel through space, they temporarily reshape it. Imagine spacetime as a taut rubber sheet, smooth and undisturbed. Now drop a heavy object onto it like a bowling ball. The sheet stretches downward, warping under the weight, but gravitational waves don't just create a single dent. They send alternating waves of stretching and squeezing rippling outward, like someone flicking the edge of the sheet rhythmically. As these waves pass through, they briefly distort distances in one direction, then the opposite, before snapping back to normal. Here's where it gets wild. These distortions are unimaginably tiny. A typical gravitational wave detected by LIGO might change the distance between Earth and the Sun by less than the width of a single atom. To put that in perspective, if you scaled Earth's orbit down to the size of a football field, the wave's effect would be smaller than the thickness of a sheet of paper. Yet, LIGO lasers can detect this microscopic wobble because they're measuring changes in distance over miles of tunnel shifts so small they'd be lost in the noise of everyday vibrations, if not for the observatory's painstaking isolation from earthquakes, trucks rumbling by, even footsteps. But don't let the scale fool you. These minuscule stretches and squeezes carry titanic meaning. Every time a gravitational wave passes through you, your body technically gets compressed in one direction and elongated in the other, but the effect is so infinitesimal you'd never notice. Even the most violent cosmic collisions, like black holes merging, only warp spacetime by a fraction of a proton's width by the time the waves reach us. That's the paradox of gravitational waves. They're born from the universe's most energetic events, yet their whispers are so faint they push our detection skills to the brink. This stretching and squeezing isn't random, it follows a precise pattern called polarization. Gravitational waves can twist spacetime in two distinct ways, like an interstellar slinky flexing side to side or up and down. These polarizations are a direct prediction of Einstein's theory, and detecting them was like finding fingerprints confirming his equations were right. Future observatories like space-based LISA might even uncover a third polarization, a twisting motion that could hint at physics beyond relativity, like hidden dimensions or new forces. So while the effect of a passing gravitational wave might seem negligible, its implications are anything but. Each tiny stretch and squeeze is a coded message, telling us not just about the black holes or neutron stars that created it, but about the very fabric of reality they're rippling through. It's as if the universe is sending us secret signals, written in the language of warped space itself, one infinitesimal distortion at a time. LIGO detectors aren't just precise, they're arguably the most sensitive measuring devices ever built by humans. Picture two identical tunnels, each stretching 2.5 miles long, arranged in a perfect L shape. Inside these vacuum-sealed tubes, laser beams race back and forth, bouncing between mirrors so finely polished they're among the smoothest surfaces on Earth. The lasers don't just travel in straight lines, they interfere with each other, creating patterns so exact that scientists can detect shifts in their alignment smaller than 1/10,000th the width of a proton. To put that absurd sensitivity into perspective, it's like measuring the distance to Alpha Centauri, the closest star system to our Sun, over 4 light-years away, with an accuracy equal to the thickness of a single human hair. The engineering behind this feat borders on the miraculous. Every component of LIGO is designed to eliminate interference from anything but gravitational waves. The mirrors, weighing 40 kilograms each, hang from glass fibers thinner than a spider's silk, isolating them from Earth's vibrations. The laser beams travel in vacuum tubes with air pressure 1 trillion times lower than our atmosphere, ensuring not even stray molecules disrupt their path. Even then, the system must filter out seismic noise from earthquakes thousands of miles away, trucks rumbling on distant highways, even the subtle pull of ocean tides flexing the planet's crust. But the real magic lies in how LIGO exploits the nature of light itself. When a gravitational wave passes through the detector, it alternately stretches one arm while squeezing the other, changing the distance the lasers travel by that minuscule proton-scale fraction. This shift alters how the light waves interfere, brightening or dimming the combined beam in a pattern that reveals the wave's origin, strength, and even the direction it came from. It's like listening for a whisper in a hurricane. The signal is buried under mountains of noise, but LIGO algorithms honed by decades of research can extract it with surgical precision. What makes this sensitivity staggering isn't just the technical achievement, it's the universe it's unlocked. Before LIGO, we could only observe cosmic events that emitted light. Now we're effectively feeling the fabric of spacetime itself tremble, picking up vibrations from collisions so distant their light hasn't reached us yet. Every tweak to LIGO design, every reduction in noise, opens a wider window into the dark, violent corners of the cosmos where gravity reigns supreme. And this is just the beginning. Future upgrades could make these detectors 10 times more sensitive, tuning our ears to whispers from the edge of the universe. If the universe were a giant bell, black hole collisions would be the clapper striking its sides. And what LIGO has revealed is that this cosmic bell rings constantly. On average, gravitational wave observatories detect a black hole merger once every week. That's right, somewhere out there, roughly every 7 days, two monstrous black holes spiral into each other with enough force to briefly outshine the entire observable universe. Wrap your mind around that for a moment. These aren't rare, once-in-a-lifetime events. They're happening all around us in every direction at a pace that suggests the cosmos is far more chaotic and violent than we ever suspected. The sheer frequency of these mergers paints an astonishing picture. Imagine standing in a forest where every few minutes, two giant trees somewhere in the distance crash together with enough force to shake the ground beneath you. Now replace those trees with black holes, some weighing dozens of times more than our Sun, and the forest with the vast expanse of the universe. That's the chorus LIGO is picking up. Scientists call it the stochastic background, a constant hum of gravitational waves from countless mergers too distant or faint to distinguish individually. Together, they create a kind of cosmic static, like hearing the overlapping murmurs of a crowded room from far away. What's truly staggering is how this changes our view of the universe. Before gravitational wave astronomy, we assumed black hole mergers were exceptional, dramatic rarities. Now we know they're commonplace, so frequent that if you could hear gravitational waves directly, the universe would sound like a never-ending drumroll of distant collisions. Some of these events involve black holes so massive they defy expectations, like the merger detected in 2019 between two black holes weighing 85 and 66 solar masses, an encounter that created a final black hole over 140 times the mass of our Sun. This symphony of collisions isn't just background noise, it's a treasure trove of data. By analyzing the rate and properties of these mergers, scientists can estimate how many black holes lurk unseen in the cosmos, how they pair up, and even how the universe's expansion affects their detection. Some theories suggest early universes might have been packed with primordial black holes, creating a cacophony of mergers we're only now beginning to hear. Others speculate that these frequent collisions could hint at exotic physics, like black holes born from collapsed dark matter or strange stellar environments that force them together. The takeaway: the cosmos isn't just violent in isolated pockets, it's alive with collisions, a grand, relentless ballet of gravity playing out in the dark. And with every new detection, we're not just adding to a catalogue of events, we're tuning our ears to the rhythm of the universe itself, one earth-shaking merger at a time. Some black holes defy the rules, not just breaking them, but rewriting them entirely. Take GW190521, the gravitational wave signal that left scientists speechless. Here's why. It came from two black holes weighing 85 and 66 times the mass of our Sun. On paper, that might not sound shocking, but these monsters shouldn't exist. According to everything we know about stellar evolution, black holes this massive can't form from dying stars alone. Here's the problem. When a massive star runs out of fuel, its core collapses into a black hole, but there's a catch. If the star's core is between about 65 and 130 solar masses, it undergoes something called pair instability. Instead of collapsing neatly, the star's core becomes so hot it starts producing matter and antimatter pairs. This triggers a runaway thermonuclear explosion so violent it obliterates the star completely, leaving nothing behind. No black hole, no remnant, just stardust scattered into space. That means black holes in this mass range, like the 85 solar mass behemoth in GW190521, shouldn't be possible. Yet LIGO detected them merging over 7 billion light-years away. So how did these cosmic rule breakers form? One leading theory is they're not first-generation black holes at all, but the products of earlier mergers. Picture two smaller black holes colliding in a dense stellar environment, like the heart of a globular cluster. Their merger creates a single, heavier black hole, which then pairs up with another and merges again, a gravitational game of cosmic billiards that could build up mass over time. Another wild possibility: these black holes might be primordial, forged not from stars but in the chaotic aftermath of the Big Bang itself, when the universe was so dense that pockets of matter could collapse directly into black holes. Then there's the final puzzle. The merged black hole weighed a staggering 142 solar masses, placing it squarely in the intermediate mass category, a rare class of black holes heavier than those formed by stars but lighter than the supermassive giants at galactic centers. Before GW 190521, intermediate mass black holes were mostly theoretical, like missing links in the cosmic food chain. Now we have direct evidence they exist, and they might be built through violent mergers like this one. The implications ripple far beyond a single detection. If black holes can grow this large through repeated mergers, it could explain how supermassive black holes got their start in the early universe. It might also mean the cosmos is littered with black holes that bypassed stellar origins entirely, lurking unseen in the darkness. Every time we catch one of these impossible collisions, it's not just a discovery, it's a reminder that the universe thrives on rewriting its own rules, and we're only beginning to decode them. Gravitational waves might be more than just ripples in spacetime. They could be our first tangible clue to hidden dimensions beyond the four we know. According to string theory, the universe might have as many as 10 or 11 dimensions, with all but our familiar four curled up so tightly they're invisible. Here's where things get wild. If these extra dimensions exist, gravitational waves could be subtly influenced by them, carrying faint fingerprints of realms we can't yet see. Imagine dropping a pebble into a pond. The ripples spread smoothly across the surface. Now imagine that same pond has unseen currents beneath, tugging at the ripples in ways you can't observe directly. That's what extra dimensions might do to gravitational waves. If the fabric of spacetime has hidden folds or wrinkles, these waves could stretch, dampen, or even echo in unexpected ways as they travel. Future detectors like Europe's planned Einstein telescope or space-based LISA might catch these anomalies, tiny deviations from Einstein's predictions that could point to dimensions just a hair's breadth away from our own. String theorists propose some mind-bending possibilities. One idea suggests gravitational waves could leak into extra dimensions, losing energy as they propagate across the cosmos. This would make waves from distant mergers slightly weaker than expected, a telltale sign of dimensions siphoning off their strength. Another hypothesis involves higher dimensional gravity behaving differently at small scales, potentially altering how black holes vibrate during collisions. The ring-down phase, where merged black holes settle into their final form, could carry faint oscillations hinting at physics beyond our four-dimensional reality. Even more tantalizing, some models suggest extra dimensions might amplify certain gravitational wave frequencies, creating unexpected resonances in the data. It's like tuning a radio and suddenly hearing a station you didn't know existed. If detectors spot these anomalies, we might not just confirm hidden dimensions, we could map their size and shape based on how they distort spacetime's ripples. The hunt for these clues is already underway. Researchers are combing through LIGO existing data, searching for statistical quirks that current theories can't explain. Future upgrades could turn gravitational wave astronomy into a precision tool for probing the universe's most elusive secrets, from extra dimensions to quantum gravity. Every wave we detect isn't just a message from colliding black holes. It's a coded telegram from the deepest layers of reality waiting to be deciphered. Gravitational waves are more than just cosmic messengers. They're the universe's most precise measuring tape. Scientists call them standard sirens, a term that might sound poetic but carries groundbreaking scientific weight. Here's why: when two compact objects like neutron stars or black holes spiral toward collision, their gravitational waves encode an incredibly accurate distance measurement. Unlike light-based methods, which rely on interpreting brightness or redshift, these waves tell us exactly how far away the merger occurred based purely on the physics of their dance. Imagine having a car horn that not only makes noise but also broadcasts its exact distance from you. That's essentially what cosmic sirens do. This matters because astronomers have been wrestling with a puzzling discrepancy in cosmology, the Hubble tension. For decades, we've had two primary ways to measure how fast the universe is expanding. One method studies nearby galaxies and supernova, while the other examines the cosmic microwave background, the afterglow of the Big Bang. The problem: these approaches give slightly different answers, off by about 6 to 8%. That might not sound like much, but in cosmology, it's equivalent to discovering your car's speedometer and GPS disagree on whether you're speeding. Something fundamental must be wrong with our understanding. Enter gravitational waves. When LIGO and Virgo detected the neutron star collision GW170817 in 2017, they didn't just record the waves, they pinpointed the event's host galaxy. By combining the wave-based distance with the galaxy's redshift, how much its light stretched as the universe expanded, scientists calculated the Hubble constant independently, free from the assumptions plaguing other methods. The result landed intriguingly between the two competing values, like a referee splitting the difference in a cosmic standoff. What makes standard sirens so revolutionary is their directness. Traditional distance measurements are like trying to gauge how far away a lighthouse is by assuming all lighthouses have identical brightness. You might get close, but variables like fog or faulty bulbs introduce errors. Gravitational waves skip those assumptions entirely. The amplitude of the waves tells us the distance directly, while the changing frequency reveals how fast the objects were orbiting before merging. It's like having the universe hand us a ruler stamped with its own units. Future detections will sharpen this tool to razor precision. With more neutron star collisions, especially those accompanied by visible light, we'll build a catalog of sirens across vast cosmic distances. Space-based observatories like LISA will extend our hearing range to mergers of supermassive black holes, whose waves could reveal how expansion rates changed over billions of years. Some theories even suggest this data might uncover whether dark energy, the mysterious force accelerating the universe's expansion, has changed over time. The implications go beyond settling academic debates. If gravitational waves confirm one Hubble value over the other, it could mean our standard model of cosmology is incomplete, perhaps requiring new physics like exotic dark matter or modifications to Einstein's gravity. Every new siren we detect isn't just adding a data point, it's tuning our ears to the universe's actual heartbeat, letting us measure reality without the filter of assumptions. In the grand quest to understand cosmic expansion, gravitational waves have handed us something priceless, an unfiltered voice in the dark. The Big Bang wasn't silent, it was a thunderclap echoing across the newborn universe, and its gravitational waves might still be ringing today. These are the primordial waves, the faintest tremors imaginable, born not from colliding black holes, but from cosmic inflation, the explosive expansion of space itself in the first trillionth of a second after creation. Detecting them would be like finding the universe's birth certificate, a direct snapshot of reality before even light had time to exist. Inflation theory suggests that during this unimaginably brief moment, the universe ballooned from smaller than an atom to the size of a grapefruit, seeding the structures we see today: galaxies, clusters, the cosmic web. This violent stretching of spacetime should have generated gravitational waves with unique properties, not the sharp chirps of black hole mergers, but a broad, constant hum permeating all of reality. Think of it as the cosmic microwave background's deeper, older cousin, a whisper from the very edge of time. The hunt for these primordial waves hinges on their imprint on the cosmic microwave background, the afterglow of the Big Bang. As inflation's gravitational waves rippled through the early universe, they subtly polarized the CMB's light in a distinctive swirling pattern called B modes. Spotting this fingerprint would confirm inflation and reveal the energy scale at which it occurred, clues about what powered the universe's birth. It's the holy grail of cosmology because it could bridge Einstein's relativity with quantum mechanics, showing how gravity behaved when all forces were one. Future missions like the space-based Light Bird or the ground-based Simons Observatory are being designed with this goal in mind. Their ultra-sensitive detectors will scan the CMB for B modes with precision far beyond current telescopes, peeling back layers of interference from dust and galactic magnetic fields. Some theorists even speculate that advanced gravitational wave detectors, like a third-generation LIGO or a future atomic interferometer in space, might catch these waves directly, a signal so ancient it would make the black hole mergers we detect now seem like yesterday's news. The implications would rewrite textbooks. Primordial waves could reveal whether the universe underwent multiple inflation phases or if other universes exist beyond our own. They might hint at quantum gravity effects where spacetime itself behaves like a frothing sea at the smallest scales. Most profoundly, they'd give us a time machine to the moment physics as we know it began, an echo from the dawn of everything waiting to be heard. Gravitational waves don't just bend space, they twist time itself. Think of spacetime as a stretchy fabric where distance and duration are woven together. When a gravitational wave passes through, it doesn't merely squeeze the fabric horizontally. It tugs at the very threads of time, making clocks tick differently depending on where they're placed. Picture two identical atomic clocks perfectly synchronized, sitting a few miles apart. As the wave rolls through, one clock might momentarily speed up while the other slows down, as if time itself is breathing in and out with the universe's rhythm. This time warping isn't science fiction, it's a direct consequence of Einstein's relativity. Just as the wave stretches space in one direction and compresses it in another, it also creates tiny, fleeting distortions in the flow of time. The effect is vanishingly small for waves we detect today, maybe a few thousandths of a trillionth of a second over Earth's diameter, but the principle is profound. If you could stand next to a merging black hole, the time dilation would be extreme. Hours for you might pass as seconds for someone far away. Gravitational waves carry that same time-bending potential, just diluted across cosmic distances. Here's where it gets even stranger. These temporal ripples aren't uniform. The wave's polarization, the way it twists spacetime, means time doesn't just speed up or slow down evenly. It does so in a pattern, like a dance where some regions rush forward while others lag behind. This asymmetry could one day let us probe the nature of gravity itself. If future detectors catch time distortions that don't match Einstein's predictions, it might hint at new physics, extra dimensions, quantum gravity effects, or even flaws in relativity. Imagine the practical implications. Precision timing systems like those governing GPS satellites already account for Earth's gravity, slowing time slightly. In a future where gravitational wave astronomy is routine, we might need to correct for these cosmic hiccups too, adjusting clocks whenever a distant black hole collision sends its time-warping whisper our way. It's a reminder that the universe isn't just a static stage. It's a dynamic, rippling fabric where even time is fluid, bending to the whims of gravity's most violent symphonies. Some gravitational waves don't just ripple, they sing. When scientists convert the raw data from mergers into sound, the signals transform into something hauntingly beautiful, cosmic chirps that rise in pitch and volume before abruptly cutting off. Picture a distant bird call, but one where the bird is a pair of black holes orbiting each other at half the speed of light, their gravitational waves shifting from a low hum to a shriek in milliseconds. These chirps aren't just artistic interpretations, they're precise sonic fingerprints of death spirals happening millions or even billions of light years away. The physics behind these sounds is as elegant as it is violent. As two black holes or neutron stars circle each other, they lose energy through gravitational waves, drawing closer with each orbit. This dance accelerates in a runaway process called in-spiral, where the frequency of the waves increases along with their amplitude, the cosmic equivalent of a spinning figure skater pulling in their arms to go faster. Initially, the signal is a faint, low-frequency rumble, almost inaudible. But as the objects get closer, the pitch rises sharply, while the volume swells like an approaching ambulance siren. The crescendo peaks at the moment of merger, followed by a rapid fade as the newly formed black hole settles into silence. LIGO team didn't just stumble onto this audio trick, it's a vital tool for understanding mergers. Human hearing is remarkably good at picking out patterns in frequency changes, often better than staring at squiggles on a graph. By sonifying the data, researchers can instantly recognize subtle features in the waves. A wobble in the chirp might hint at one black hole spinning wildly, while an asymmetrical rise could suggest the objects had drastically different masses. Some chirps even reveal surprises, like a neutron star's crushing transformation into a black hole mid-collision, its final moments marked by a brief, high-pitched squeak before the signal winks out. The eeriest part, these chirps aren't just scientific abstractions, they're real sounds you can listen to right now. LIGO website hosts clips of actual detections, from the deep, guttural growl of two heavy black holes merging to the bright, metallic ping of neutron stars colliding. One particularly haunting example, GW150914, starts as a basso profundo murmur before leaping to a treble climax, a sonic snapshot of 230 solar mass black holes merging over 1 billion years ago. Another, GW170817, pairs the chirp with the actual gamma ray burst it triggered, blending gravity's whisper with light's thunder. These sounds do more than captivate, they redefine how we experience the cosmos. Before gravitational wave astronomy, the universe was silent, a realm we explored with eyes alone. Now we've unlocked its soundtrack, a chorus of chirps and rumbles telling stories no telescope could ever see. Every chirp is a lifeline to an event so distant, so alien, we'd have no other way to witness it. And as detectors grow more sensitive, the symphony will only grow richer, filling in the gaps of a universe that's been singing to us all along. We just needed the right ears to hear it. When black holes collide, they don't always play fair sometimes. The merger isn't a perfect union, but a cosmic shove so violent it can launch the resulting black hole across the universe at mind-blowing speeds. Scientists call these events black hole kicks, and they're among the most extreme phenomena in astrophysics. Picture two black holes spiraling toward each other. If their merger isn't perfectly symmetrical, perhaps due to mismatched masses or wildly different spins, the gravitational waves they emit can carry momentum in one direction like a rocket exhaust. The result, a recoil effect so powerful it can eject the newborn black hole at speeds exceeding 5 million miles per hour, fast enough to escape its host galaxy entirely. Take GW200129, a gravitational wave detection from January 2021. Analysis suggested this merger might have sent its resulting black hole hurtling through space at nearly 3 million miles per hour. The evidence lies in the waves themselves. Subtle asymmetries in their pattern hinted at an uneven release of energy during the collision, like a fire hose blasting sideways instead of spraying evenly. If confirmed, this would mark the first direct observation of a black hole kick, proving these cosmic catapults aren't just theoretical. The physics behind these kicks is as elegant as it is violent. When two black holes merge, the final object typically settles down via ring down, emitting gravitational waves symmetrically in all directions. But if the pair had lopsided spins or masses, the waves can carry away momentum preferentially in one direction, thrusting the black hole opposite that recoil. It's Newton's third law in action. For every action, there's an equal and opposite reaction, except here, the action is spacetime itself being violently stirred. These kicks have staggering cosmic consequences. a black hole ejected from its galaxy becomes a rogue wanderer drifting forever through the intergalactic void. For smaller black holes, that might mean a lonely existence in the darkness, but for supermassive ones, the kind found at galactic centers, a kick could strip a galaxy of its gravitational anchor, disrupting star formation and leaving behind a galactic husk. Some astronomers even speculate that the universe might be filled with nomad black holes, invisible and undetectable except by the rare gravitational lensing event or chance encounter with a star. Yet detecting these kicks is fiendishly hard. The telltale signatures in gravitational waves are minuscule, buried in the data's noise. Future observatories like LISA, with its precision for low-frequency waves, could spot supermassive black holes recoiling during mergers, events so powerful they'd send their victims flying at tens of millions of miles per hour. Until then, every potential kick detection, like GW200129, offers a tantalizing glimpse into the universe's most dramatic escape acts, where the aftermath of a collision isn't just a bigger black hole, but a celestial bullet fired into the endless dark. Even the most advanced gravitational wave detectors face an invisible enemy, one that shakes the very fabric of reality at the smallest scales. Quantum mechanics, the bizarre rulebook governing particles, introduces a fundamental limit to how precisely we can measure spacetime's ripples. This isn't just background noise, it's a ceaseless jittering at the quantum level, where empty space itself bubbles with virtual particles flickering in and out of existence. Picture trying to measure the height of a mountain while standing on a trampoline being randomly jostled by unseen hands. That's the challenge quantum noise poses to detectors like LIGO. At the heart of this problem lies Heisenberg's uncertainty principle, which states that certain pairs of physical properties, like a particle's position and momentum, can't both be measured perfectly at the same time. For gravitational wave detectors, this translates to shot noise, random fluctuations in the laser photons used to measure mirror positions. Even in perfect vacuum conditions, these quantum fluctuations blur measurements at scales smaller than an atom, masking the faint whispers of distant black hole mergers. To combat this, scientists turn to one of quantum mechanics' most counterintuitive phenomena, squeezed light. Normally, laser light carries equal uncertainty in its phase and amplitude, but by squeezing the light, researchers can reduce noise in one property at the expense of the other, like trading clarity on the x-axis for fuzziness on the y-axis. Imagine tuning a radio by deliberately muffling static in the frequency you care about, even if it makes other channels noisier. LIGO squeezed light setup does precisely this, redistributing quantum uncertainty to minimize the noise affecting gravitational wave measurements. The results are astounding. By injecting this specially engineered light into their detectors, LIGO team boosted sensitivity by up to 50%, allowing them to peer deeper into the cosmos than ever before. Future upgrades could push this further, potentially using quantum entanglement to link photons in ways that bypass Heisenberg's limits entirely. It's a cosmic irony that the very quantum laws obstructing our measurements might also hold the key to surpassing them, turning physics' greatest quirks into humanity's sharpest tools for listening to the universe. But quantum noise isn't the only hurdle. Thermal vibrations in detector materials, the faint pressure of laser photons hitting mirrors, even the ghostly pull of cosmic rays, all conspire to obscure gravitational wave signals. Each time scientists conquer one noise source, another emerges from the shadows like peeling layers from an infinite onion. Yet with every innovation, from cryogenically cooled mirrors to AI-driven noise filtering, we're not just building better detectors, we're learning to read the universe's faintest handwriting, scribbled in the shaky script of quantum uncertainty. Among all the bizarre objects theorized in physics, cosmic strings might be the strangest. Not black holes, not neutron stars, but literal cracks in the fabric of reality itself. Picture the universe in its earliest moments, still seething with the energy of creation. As it expanded and cooled, spacetime itself might have developed flaws like imperfections in a rapidly freezing ice sheet. These one-dimensional defects, thinner than a proton but stretching across light years, would carry unimaginable density. Just a single inch of cosmic string could outweigh Mount Everest. And if they exist, their violent movements could send gravitational waves rippling through the cosmos like cracks echoing through a frozen lake. Unlike the smooth, chirping waves from black hole mergers, a snapping cosmic string would produce something far more abrupt, a gravitational wave burst. Imagine plucking a guitar string so violently it snaps mid-vibration, releasing a sharp, discordant twang. That's the kind of signal scientists are hunting for, a sudden spike in the data, potentially lasting just milliseconds but packing enough energy to outshine entire galaxies. These bursts wouldn't come from collisions or explosions, but from the strings themselves vibrating, intersecting, or even breaking apart in a process called reconnection. When two segments of string cross, they could slice through each other, sending out shockwaves in spacetime or forming closed loops that oscillate wildly before vanishing in a puff of gravitational radiation. The hunt for these cosmic cracks isn't just theoretical fantasy. Some models suggest that if strings exist, their gravitational waves could fall within the detection range of current observatories like LIGO or future ones like the Einstein telescope. The challenge: distinguishing them from background noise. Black hole mergers follow predictable patterns, their waveforms sculpted by Einstein's equations. Cosmic string bursts, though, would be far more chaotic, unique fingerprints of spacetime itself fraying at the edges. Detecting one would be like hearing a single discordant note in a symphony and realizing it's the sound of the violin strings splitting apart. What makes cosmic strings so tantalizing isn't just their weirdness, it's what they'd reveal about the universe's infancy. Their existence would confirm that spacetime underwent phase transitions in its earliest moments, freezing into structures like cosmic frost forming on a window. Some theories even suggest these strings could be time capsules, preserving conditions from the first trillionth of a second after the Big Bang, when all the fundamental forces were still unified. Finding one would give us a direct line to an era so remote, even light from that time has long since faded into oblivion. And then there's the wildest possibility of all: cosmic strings might not just be relics of the past. Some speculative models propose they could still be forming today in the hearts of extreme environments, like near supermassive black holes or in the aftermath of high-energy particle collisions. If true, the universe could be threaded with invisible, vibrating scars, each one a potential source of gravitational waves we've only begun to imagine. Every snap, every oscillation would be a message from the edge of physics, where the fabric of reality isn't just bending, it's fraying. Gravitational waves don't just travel in straight lines, they can bend and warp around massive objects just like light. This phenomenon, called gravitational lensing, turns the fabric of spacetime itself into a cosmic funhouse mirror, twisting and amplifying the signals from distant collisions in ways that can make a single cataclysmic event appear multiple times in our detectors. Think of it like an echo in a vast cavern where the original shout bounces off walls, reaching your ears from different directions at slightly different times. Only here, the walls are galaxies or black holes so massive they warp the paths of gravitational waves passing by. The mechanics behind this are mind-bending. When a gravitational wave encounters a massive object, say, a galaxy cluster weighing as much as 1,000,000 billion suns, the object's gravity acts like a lens, bending the wave's trajectory. Depending on the alignment, this can split the signal into multiple paths, each curving around the lens at different angles before reaching Earth days, weeks, or even years apart. It's as if the universe hit the replay button on a black hole merger, giving us multiple chances to study the same event from slightly different cosmic perspectives. LIGO might have already recorded lensed waves without realizing it, Take GW190521, the puzzling merger of two black holes with impossible masses. Some theorists speculate this signal could actually be a lensed echo of an earlier, unseen collision, its waveform stretched and duplicated by a massive object between us and the source. If true, it would mean we're not just detecting these waves, we're seeing them reflected through the universe's own gravitational hall of mirrors. The implications are staggering. Lensed waves could act as cosmic telescopes, magnifying faint signals from the early universe that would otherwise be too weak to detect. They might also reveal hidden masses, dark matter halos, or rogue black holes by the way they distort passing ripples. Future observatories with even greater sensitivity could turn this effect into a precision tool, mapping the distribution of mass across the cosmos by studying how it warps gravitational wavefronts. But the real magic lies in what lensing could teach us about spacetime itself. If we catch a wave being lensed by a supermassive black hole, the subtle delays between its multiple arrivals would let us measure the black hole's mass with unprecedented accuracy. Some theories even suggest lensing could expose exotic physics like wormholes or quantum foam, if their gravitational fingerprints alter the waves in unexpected ways. Every lensed signal isn't just a replay, it's a chance to see the universe's hidden architecture through gravity's own warped lens. Every gravitational wave is like a cosmic fingerprint, each one uniquely shaped by the violent event that created it. When black holes or neutron stars collide, the ripples they send racing through spacetime aren't random. They're meticulously structured, carrying encoded details about the object's masses, how fast they were spinning, even the precise angle of their orbits. It's as if the universe broadcasts a forensic report with each merger, and scientists have learned to decode it. Take the distinctive chirp pattern LIGO detects. That rising frequency isn't just a dramatic soundtrack, it's a direct translation of the object's final death spiral. The steeper the chirp, the more massive the colliding objects. The duration of the signal reveals how long they orbited before merging. Even subtle wobbles in the waveform can betray whether one black hole was spinning like a top, dragging space-time around with it in a whirlpool effect. Researchers feed these nuances into supercomputers running Einstein's equations backward, effectively reconstructing events that happened billions of years ago with shocking precision. For example, when LIGO detected GW150914, the wave's shape immediately revealed the black holes weighed roughly 36 and 29 solar masses. Their spins were misaligned, suggesting they might have formed separately before being thrown together in a dense stellar environment. The signal's asymmetry even hinted at their orbital planes' tilt relative to Earth. It's like deducing the size, swing, and impact angle of two baseball bats just by listening to the crack they make when they collide, except these bats were warped spacetime monsters over 1 billion light-years away. Neutron star mergers tell even richer stories. Their waves often show telltale distortions caused by tidal forces the moment when one star's gravity starts shredding its partner before impact. These fingerprints can reveal properties like the star's internal composition, how squishy their ultra-dense matter is, and even whether the collision left behind a black hole or a temporary hypermassive neutron star. When GW170817's waves were analyzed, they showed the neutron stars were likely around 1.4 solar masses each, with one possibly being slightly deformed by its partner's gravity seconds before merging. What makes this decoding possible is how exquisitely gravitational waves couple to their sources. Unlike light, which often interacts with matter in complex ways, scattering, absorbing, or changing color, these spacetime ripples emerge pristine, reflecting only the dynamics of gravity itself. A single waveform can contain hundreds of overlapping harmonics, each a clue waiting to be extracted. Advanced algorithms now parse these signals to distinguish between mergers involving black holes with slow, lazy spins versus those whirling near light speed, or between neutron stars with crisp, hard surfaces versus those with molten outer layers. This isn't just academic sleuthing, it's revolutionizing how we understand cosmic populations. By tallying the masses and spins of hundreds of detected mergers, scientists are building a census of black holes and neutron stars, uncovering surprising trends. Why are there so many black holes clustered around 40 solar masses, a size rarely seen in traditional astronomy? How do some neutron stars end up so perfectly matched in mass? Each wave's encoded story adds another piece to the puzzle, painting a picture of how these objects form, pair up, and collide across the universe's history. The most astonishing part, we're just beginning to read this gravitational Rosetta Stone, and every new detection teaches us to decipher deeper layers of the universe's hidden narratives. While LIGO and its successors scan the cosmos for high-frequency gravitational waves, another network of detectors is quietly listening to the universe's deepest bass notes using dead stars as their instruments. Enter pulsar timing arrays, one of the most ingenious ways scientists are hunting for gravitational waves at frequencies too low for traditional detectors to catch. These arrays don't rely on lasers or vacuum chambers. Instead, they harness the cosmic precision of pulsars, rapidly spinning neutron stars that beam radiation like interstellar lighthouses with metronomic regularity. Some of these pulsars spin hundreds of times per second, their radio pulses arriving on Earth with a consistency rivaling atomic clocks. But when a gravitational wave passes through, it can stretch and compress the space between us and the pulsar, causing those once perfect ticks to arrive slightly early or late. It's like detecting a gust of wind by watching how it disrupts the steady rhythm of a ticking pocket watch suspended in midair. What makes pulsar timing arrays so powerful is the scale of waves they're designed to catch. While LIGO detects chirps from stellar mass black holes lasting seconds, these arrays hunt for waves with periods of years, ripples so long they could stretch from Earth to the Sun and back. The prime suspects, supermassive black hole binaries, pairs of billion solar mass monsters circling each other in the cores of distant galaxies. As these colossal objects spiral closer over millennia, they generate gravitational waves at frequencies too low for LIGO but perfect for pulsar timing's patient gaze. Picture two whales singing in the ocean's depths. Their songs are too bass-heavy for a microphone designed to catch dolphin clicks, but spread out a net of underwater sensors, and suddenly those rumbles become impossible to miss. That's what pulsar timing arrays do for the low-frequency gravitational wave spectrum. The technology behind this method is as elegant as it is simple in principle. By monitoring dozens of pulsars scattered across our galaxy, each acting as an independent gravitational wave sensor, scientists can look for correlated timing glitches that betray a passing wave. Imagine a field of flags fluttering in the wind. If one flag moves, it might just be local turbulence, but if all suddenly sway in unison, you know a larger disturbance has passed through. Current arrays like NanoGrav in North America, the European Pulsar Timing Array, and Australia's Parkes Pulsar Timing Array have been collecting data for over a decade, and in 2023 they unveiled tantalizing evidence of a possible gravitational wave background. A chorus of murmurs from countless supermassive black hole pairs scattered across cosmic history. This background isn't the sharp chirp of a single merger, but more like the static hiss of a detuned radio, the combined hum of every supermassive binary in the universe. Analyzing it could reveal populations of black holes we've never seen, map the merger history of galaxies, and even probe the universe's expansion rate over billions of years. Future upgrades, like including more pulsars or observing with next-generation radio telescopes such as the Square Kilometre Array, could turn this murmur into a clear voice, one telling us how often galaxies collide, how black holes grow, and perhaps even exposing more exotic sources like cosmic strings or phase transitions in the early universe. Every slight deviation in a pulsar's tick is a breadcrumb leading us deeper into gravity's hidden symphony. Gravitational waves might hold the key to one of cosmology's greatest puzzles, the nature of dark matter. While telescopes search for this invisible substance through its gravitational tug on galaxies, gravitational wave detectors could reveal it in a far stranger way, by catching echoes of hypothetical dark matter objects colliding or even sensing the subtle distortions they create in passing waves. Imagine dark matter not as a uniform haze, but as a population of hidden cosmic players, each leaving faint but distinctive signatures in the ripples of spacetime. One tantalizing candidate is primordial black holes, hypothetical black holes forged not from dying stars, but in the seething chaos of the early universe. These ancient relics could range in size from smaller than an atom to larger than a star, and if they exist in abundance, they might account for some or even all of dark matter. Gravitational waves offer a unique way to hunt them. When two primordial black holes merge, their collisions would produce chirps similar to those LIGO detects, but with quirks betraying their exotic origins. Unlike stellar black holes, which form from collapsing stars and thus have minimum masses, primordial black holes could be far lighter, producing higher-pitched signals that current detectors aren't tuned to catch. Future observatories like the Einstein telescope might spot these whispers, revealing a hidden population of dark matter black holes dancing through the cosmos. Then there's the possibility of actions, ghostly particles so lightweight they behave more like waves than discrete objects. In extreme environments, like around spinning black holes, actions could condense into vast, swirling clouds, distorting spacetime in peculiar ways. As these clouds interact with black holes, they might imprint faint modulations on gravitational waves, a sort of cosmic tremolo effect detectable in the wave's structure. It's as if the black hole is ringing like a bell wrapped in a gauzy action veil, its vibrations subtly muffled or altered. But the wildest theories suggest dark matter itself could generate gravitational waves directly. If dark matter consists of cosmic strings, those hypothetical spacetime defects, their snaps and vibrations would send out bursts of gravitational radiation, unlike anything from black holes or neutron stars. Even more exotic ideas propose dark matter particles so massive that their quantum fluctuations create microscopic ripples in spacetime, a subatomic humming woven into the fabric of reality. While these signals would be absurdly faint, next-generation detectors might one day tease them from the noise, turning gravitational wave astronomy into a dark matter microscope. The beauty of this approach is its versatility. Unlike traditional searches that rely on dark matter interacting with light or ordinary matter, gravitational waves bypass those requirements entirely. They don't care if dark matter is invisible, non-luminous, or barely touches the world we know. They only respond to gravity's pull. Every chirp, every ripple could carry encrypted clues about the universe's missing mass hidden in plain sight. And with each new detection, we're not just listening to black holes collide, we're eavesdropping on the dark universe's best-kept secrets. The quietest places on Earth aren't silent at all, they're alive with the restless thrum of our planet itself, a cacophony of vibrations that threaten to drown out the faint whispers of gravitational waves. Beneath LIGO pristine vacuum chambers and suspended mirrors, Earth never stops moving. Ocean waves crashing on distant shorelines send tremors through the crust, a relentless drumbeat pulsing at frequencies gravitational wave detectors must strain to ignore. Even human activity, trucks rumbling down highways, trains braking miles away, construction equipment pounding the ground, creates seismic static that can mask the delicate signals scientists are hunting. It's like trying to hear a pin drop in the middle of a thunderstorm. This isn't just background noise, it's an ever-shifting obstacle course for detectors. Take the microseismic peak, a constant vibration between 0.1 and 0.5 Hz caused by storms churning the ocean. These waves travel thousands of miles, transferring energy into the ground and making the Earth's surface bob like a cork on water. For LIGO, it means mirrors that should hang motionless in space are instead swaying imperceptibly, their laser measurements blurred by the planet's own heartbeat. Then there's the hum, a mysterious global oscillation between 2 and 7 millihertz, possibly driven by atmospheric turbulence or the ocean's ceaseless pressure on the seafloor. Scientists still debate its origins, but to gravitational wave hunters, it's another layer of static to filter out. The battle against this noise is fought with engineering marvels. LIGO mirrors hang from glass fibers thinner than a human hair, isolated in vacuum chambers to escape air currents. Advanced algorithms subtract known seismic patterns in real time, like noise-canceling headphones for spacetime itself. But nature keeps upping the ante. Earthquakes halfway across the globe send vibrations that can knock detectors offline for hours, while sudden glitches of unknown origin litter the data like cosmic pop-ups. One notorious event in 2019 was traced to ice cracking on a frozen river 30 miles from the observatory, proving no vibration is too small to matter. Yet this interference isn't just a nuisance, it's a paradoxical clue to Earth's inner workings. The same seismic noise that obscures gravitational waves also lets scientists map our planet's hidden structures. When a gravitational wave signal arrives slightly skewed by passing through a magma chamber or tectonic boundary, that distortion becomes a sonogram of Earth's guts. Future detectors might even use gravitational waves as probes, turning cosmic collisions into tools for geology. Until then, the hum of our living planet remains both adversary and teacher, a reminder that to hear the universe's faintest ripples, we must first learn to quiet the ground beneath our feet. The hunt for gravitational waves is about to leave Earth behind because the next generation of detectors won't just be bigger or more sensitive, they'll be orbiting the Sun. Enter LISA, the Laser Interferometer Space Antenna, a mission so ambitious it makes LIGO 4-kilometer arms look like a backyard experiment. Slated for launch in the 2030s, this trio of spacecraft will form a perfect triangle, flying 2.5 million kilometers apart with laser beams connecting them like the universe's most precise ruler. Freed from Earth's constant tremors and atmospheric interference, LISA Floating Observatory will detect gravitational waves at frequencies so low they're practically cosmic bass notes, opening a window into collisions far grander than anything we've witnessed before. What makes space the ultimate gravitational wave hunting ground isn't just the silence, it's the scale. While LIGO catches the high-pitched chirps of stellar mass black holes merging in seconds, LISA will tune into events that unfold over years, even decades. Picture 2 supermassive black holes, each weighing billions of suns, circling each other in the heart of distant galaxies. Their gravitational waves ripple outward at wavelengths so vast they could stretch from here to Jupiter, undetectable from our noisy planet. But LISA million-kilometer arms will resonate with these waves like a tuning fork, picking up the slow, rhythmic pulses as the black holes inch closer across millennia. It's the difference between hearing a mouse squeak and feeling the infrasound rumble of an approaching thunderstorm. The sources LISA could uncover read like a cosmologist's wish list. Binary white dwarfs in our own galaxy, spiraling so quietly their waves get lost in Earth's seismic din. Primordial black holes from the dawn of time humming faintly in the void. Even the possibility of cosmic strings, those hypothetical spacetime cracks vibrating like guitar strings across the universe. But the real prize, capturing the moment 2 supermassive black holes finally collide, an event so catastrophic it could warp spacetime across an entire galactic neighborhood. When that happens, LISA won't just detect a fleeting chirp, it'll record a crescendo lasting weeks or months. A symphony of warping space with enough detail to map the black hole's masses, spins, and trajectories with pinpoint accuracy. The engineering behind LISA borders on science fiction. Each spacecraft must maintain position accurate to within a few atoms, compensating for solar wind and microscopic dust impacts. The lasers, bouncing between free-floating gold-platinum cubes inside the ships, will measure distance changes smaller than the width of a helium atom over those million-kilometer spans. To test these technologies, the mission LISA Pathfinder, launched in 2015, proved it could achieve near-perfect freefall in space, a precursor to the precision needed for the full array. Beyond the spectacle, LISA data could rewrite astrophysics. By tracking how gravitational waves from supermassive binaries bend around intervening galaxies, we might map dark matter's distribution in 3D. The mission could also spot unexpected anomalies, hints of extra dimensions, deviations from Einstein's predictions, or even echoes from the Big Bang itself. It's not just an upgrade to LIGO, it's a leap into an uncharted gravitational spectrum where the universe's deepest voices finally have the stage to themselves. And when those first signals arrive, we won't just be listening to the cosmos, we'll be hearing it in a way no one ever has before. Wormholes aren't just science fiction. They might leave whispers in gravitational waves if they're hiding in the cosmos. Picture a shortcut through spacetime, a tunnel connecting two distant points like a cosmic subway. While Einstein's equations allow for such structures, known as traversable wormholes, they'd require exotic matter with negative energy to stay open. But here's the twist: if they exist, their presence could warp passing gravitational waves in ways unlike anything black holes or neutron stars produce. Imagine shouting into a pipe and hearing your voice echo back similarly. A gravitational wave passing near a wormhole might ripple through its throat and re-emerge with a slight delay, creating a faint duplicate signal trailing the original like a shadow. This echo effect wouldn't just be a subtle delay. It could carry clues about the wormhole's shape and stability. The time between the initial wave and its echo would reveal the tunnel's length, while distortions in the wave's pattern might hint at the exotic matter warping spacetime inside. Some models even suggest wormholes could act like cosmic amplifiers, bending waves in ways that boost certain frequencies. It's as if spacetime itself became a funhouse mirror, stretching and squeezing the waves into a signature no natural object could replicate. Then there's the strangest possibility. Wormholes might not just passively distort waves, they could vibrate. Like plucking a guitar string, a passing gravitational wave could excite oscillations in the wormhole's throat, creating secondary ripples at distinct frequencies. These quasi-normal modes would differ from black hole ringdowns, lacking the sharp cutoff of an event horizon. Instead, they'd fade slowly, as if the wormhole were humming a ghostly note long after the initial collision. Future detectors like LISA or the Einstein telescope could spot these anomalies, especially if a wormhole lurks near a supermassive black hole where wave amplitudes are extreme. The implications would rewrite physics. Detecting a wormhole's gravitational fingerprint wouldn't just prove their existence, it could reveal whether they're naturally occurring relics of the early universe or artifacts of advanced civilizations. Some theorists even propose that certain high-frequency gravitational wave bursts might not be black hole collisions at all, but artificial wormholes stabilizing themselves with engineered exotic matter. Far-fetched perhaps, but the universe has surprised us before. Every unexplained ripple in the data isn't just noise, it's a potential doorway to the extraordinary, waiting for us to listen closely enough. Black holes might be the ultimate testing ground for physics' greatest unsolved puzzle: how to marry Einstein's theory of gravity with the bizarre rules of quantum mechanics. When two black holes spiral toward collision, their final moments plunge into a realm where spacetime curvature becomes infinite and quantum effects should reign supreme. This is where our current theories break down, and where gravitational waves could hand us clues to something deeper. The violent ring-down phase after a merger, when the new black hole vibrates like a struck bell, might carry subtle deviations from Einstein's predictions, tiny hiccups betraying the fingerprints of quantum gravity. Take loop quantum gravity, one leading candidate to unify these disparate worlds. This theory suggests spacetime isn't smooth and continuous, but woven from microscopic loops, a pixelated reality where even black holes can't form true singularities. If correct, these loops would prevent the infinite curvature at a black hole's core, replacing it with a bounce that subtly alters how the merged black hole settles. Gravitational waves from such an event might show dampened high-frequency oscillations, like a muffled drum compared to relativity's crisp prediction. Similarly, string theory proposes extra dimensions could leak gravitational wave energy during mergers, causing certain harmonics to fade faster than expected. The challenge lies in spotting these quantum whispers amid the cosmic roar. Current detectors like LIGO aren't sensitive enough to catch such minuscule anomalies. It's like trying to hear a violin's out-of-tune string in a stadium concert. But next-generation observatories like the Einstein telescope with its tenfold sensitivity boost or space-based LISA free from Earth's noise could discern these deviations. Some models suggest quantum gravity might imprint fractal-like patterns on gravitational wave spectra, or cause delays between different polarization modes as they traverse spacetime's granular structure. Even failed detections would revolutionize physics. If black holes ring precisely as Einstein predicted down to the quantum scale, it would rule out entire classes of theories. But if we catch even a single wave behaving oddly, say, with an echo where none should exist or frequencies that defy relativity's math, it could unveil the universe's fundamental texture. Every merger we detect isn't just a cosmic collision. It's a laboratory testing physics at energies no particle accelerator could ever reach, probing the edge of reality itself. GW190521 wasn't just another gravitational wave, it was a cosmic earthquake that rewrote our understanding of black holes. On May 21, 2019, detectors picked up a signal so powerful it briefly shook the entire field of astrophysics. This was the merger of two black holes weighing 85 and 66 times the mass of our Sun. An event so violent it released energy equivalent to 8 solar masses in gravitational waves alone. The resulting black hole, a monstrous 142 solar masses, placing it squarely in the elusive intermediate mass range, the long-sought missing link between stellar mass black holes and the supermassive giants lurking in galactic centers. The sheer scale of this collision defied expectations. Most black holes detected previously fell below 50 solar masses formed from collapsing massive stars. But GW190521's heavier progenitor black holes shouldn't have existed according to standard stellar evolution models. When stars reach 65 to 130 solar masses, they typically undergo pair instability supernova explosions so violent they leave nothing behind, no remnant at all. That these black holes bypassed that fate suggests they might be second-generation products, themselves the remnants of earlier mergers in dense stellar environments. Picture a cosmic game of billiards where black holes keep colliding and growing over eons, building up mass like rolling a snowball downhill. What made this detection extraordinary wasn't just the black hole's bizarre sizes, it was how clearly they signaled a new cosmic population. Intermediate mass black holes between 100 and 100,000 solar masses had been theorized for decades, potentially serving as stepping stones to supermassive varieties. Yet they'd remained frustratingly elusive, too massive to form from single stars but too small to imprint clearly on their galactic surroundings. GW190521 changed that, delivering direct proof of their existence through gravitational waves' unambiguous testimony. The merger's waveform carried distinctive signatures of the black hole's lopsided mass ratio and rapid spins, suggesting they might have formed in a chaotic environment like a globular cluster or galactic nucleus, where frequent encounters could lead to such unusual pairings. The energy released was beyond anything previously recorded, a gravitational wave screamed so loud it briefly outshone all the stars in the observable universe combined. For a fraction of a second, the collision radiated more power than all the light from every galaxy in existence. Yet this cosmic fireworks show happened in complete darkness, invisible to telescopes, its fury expressed purely through spacetime's trembling. Future observatories like LISA might catch similar events involving even larger intermediate mass black holes, helping us map how these cosmic middleweights bridge the gap between stellar remnants and the supermassive behemoths that shape galaxies. Every extreme merger like GW190521 isn't just a record breaker, it's a puzzle piece in understanding how black holes grow across cosmic time. Gravitational waves don't just carry messages across space, they're cosmic time capsules, delivering snapshots of the universe's most violent moments directly to our detectors. When LIGO captures a ripple from a black hole collision a billion light-years away, we're not just observing an event from the distant past, we're experiencing it in real time, like watching a delayed broadcast of history's greatest hits. Imagine if, instead of studying dinosaur fossils to understand their extinction, we had a live feed of the asteroid impact. Gravitational waves offer that same visceral immediacy for cosmic cataclysms. Consider the neutron star merger detected in 2017. The waves that reached Earth had been traveling for 130 million years, meaning they originated when brachiosaurs still roamed our planet. By the time those ripples arrived, the gold forged in that collision had already been woven into the fabric of new stars, planets, and possibly even life. Yet from our perspective, the event unfolded fresh, its light and gravitational signals reaching us simultaneously like a synchronized cosmic alarm. This isn't just astronomy, it's time travel by proxy, where every detection peels back another layer of the universe's hidden chronology. The implications stretch even further into the past. Gravitational waves from the earliest epochs of the universe, if we can detect them, would let us peer past the cosmic microwave background's opaque veil back to the first trillionth of a second after the Big Bang. While light from that era was trapped in a dense plasma fog, gravitational waves slipped through unimpeded, carrying undistorted echoes of inflation's violent expansion. Future observatories might capture these primordial ripples, effectively giving us a front-row seat to creation itself, no different than tuning into a radio broadcast from the universe's first moments. What makes this time machine effect so powerful isn't just the antiquity of the events, it's their pristine preservation. A supernova's light dims as it crosses the cosmos, scattered by dust and gas. But gravitational waves, they arrive exactly as they left, their waveforms encoding every detail of the collision's final milliseconds with perfect fidelity. When we analyze the chirp of two merging black holes, we're not reconstructing their dance from fragmented clues, we're watching the actual performance frame by frame as if we'd been there. This real-time archaeology could soon rewrite cosmic history. Imagine detecting waves from population 3 stars, the universe's first, impossibly massive stars that lived fast and died young. Their collisions would imprint gravitational signatures unlike anything we've seen, offering direct evidence of how the earliest black holes formed. Or consider the faint murmurs of cosmic strings snapping in the dark, relics of phase transitions when the fundamental forces first split apart. Every wave is a time-stamped dispatch from an era we've only theorized, waiting to confirm or dismantle our models of cosmic evolution, the most profound revelation. Gravitational waves don't just show us the past, they force us to confront the fluidity of time itself. When a wave from a distant merger warps spacetime on its way to Earth, it briefly alters the flow of time in its path, creating a kind of temporal lens. Future detectors might exploit this effect to measure the universe's expansion rate directly, comparing how waves from ancient collisions were stretched or compressed en route. It's as if the waves themselves are clocks ticking unevenly across billions of years, each chirp a synchronized reminder that time isn't absolute, but a malleable thread woven through the cosmos's fabric. For billions of years, the universe has been telling its story through gravitational waves, ripples carrying tales of colliding black holes, dying stars, and perhaps even echoes of its fiery birth. But until recently, there was no one to listen. That changed on September 14, 2015, when humanity finally joined this cosmic conversation, transforming Einstein's century-old equations from abstract theory into something we could measure, analyze, and even hear. This wasn't just a scientific achievement, it was a profound shift in our relationship with the cosmos, proving we're no longer passive observers, but active participants in unraveling the universe's deepest secrets. Consider what this means. Every time LIGO or Virgo detects a gravitational wave, we're essentially intercepting a message sent millions or even billions of years ago, a fragment of history traveling at light speed to reach us. These signals aren't altered by cosmic dust or distorted by magnetic fields. They arrive exactly as they left their source, pristine and undistorted. It's as if the universe handed us a direct line to its most violent events, bypassing the limitations of light-based astronomy entirely. Where telescopes show us snapshots of celestial objects, gravitational waves let us feel the universe's vibrations, like placing a stethoscope against the heart of spacetime itself. This new sense has already rewritten cosmic narratives. Before 2015, black hole mergers were theoretical possibilities. Now we know they happen weekly. Neutron star collisions were assumed to forge heavy elements, then GW 170817 proved it in spectacular fashion. Even the basic tools of science have transformed. Where astronomers once relied solely on photons, they now analyze waveforms with the same expertise a musician uses to identify instruments by ear. The chirp of merging black holes has become as recognizable as the ring of a familiar voice, each one revealing new extremes of mass, spin, and cosmic violence. But beyond the discoveries lies something deeper, a philosophical shift in how we perceive our place in the cosmos. Gravitational waves connect us to events so distant, so alien, they defy human scales of time and space. When we detect a collision that occurred before multicellular life existed on Earth, we're not just collecting data, we're bearing witness to a universe indifferent to our existence, yet suddenly intimately knowable. This duality of cosmic grandeur and scientific mastery is what makes gravitational wave astronomy so transformative. We're no longer creatures peering at the night sky in wonder. We've become listeners decoding the universe's hidden language, one ripple at a time. The most astonishing part, this is just the beginning. As detectors grow more sensitive and new observatories like LISA come online, we'll hear fainter whispers from further back in time, perhaps even catching the tremors of the Big Bang itself. Future generations might look back on this era as the moment humanity truly began to converse with the cosmos, not through passive observation, but by learning to interpret the subtle vibrations of spacetime's fabric. Every new detection adds another verse to this ongoing dialogue, reminding us that the universe isn't just out there, it's speaking if we're willing to listen. From Einstein's bold prediction in 1916 to LIGO groundbreaking detection in 2015, gravitational waves have shattered our understanding of the cosmos. We've explored 30 astonishing facts: how spacetime ripples travel at light speed untouched by matter, how colliding black holes briefly outshine the entire universe, and how neutron star mergers forge gold in cosmic fire. We've decoded chirps from cosmic collisions, imagined wormholes echoing through dimensions, and glimpsed primordial waves that could carry whispers from the Big Bang itself. Each discovery peels back another layer of reality, revealing a universe far stranger than we ever dreamed. Think about what we've witnessed: black holes catapulted across galaxies at millions of miles per hour, dark matter's hidden fingerprints etched into gravitational signals, quantum whispers warping spacetime itself. These aren't just scientific triumphs, they're invitations to wonder. When LIGO caught its first wave, humanity didn't just prove Einstein right, we gained a new sense, one that lets us feel the universe's heartbeat through the fabric of reality. The journey's far from over. With Lisa million-kilometer space antennas, pulsar timing arrays listening for cosmic bass notes, and next-gen detectors hunting quantum gravity signatures, every new tool promises revelations we can't yet imagine. Will we hear echoes from cosmic strings, decode the birth cries of time, discover hidden dimensions woven into spacetime's ripples? The beauty lies in the unanswered questions. Each gravitational wave is a mystery waiting to unfold, a story half told in the language of warped space and twisted time. So tell us, which fact left you awestruck? Was it the black holes that shouldn't exist, the gold forged in neutron star collisions, or the cosmic time machine letting us witness ancient cataclysms in real time? Drop your favorite in the comments, and if you're hungry for more cosmic wonders, hit subscribe. Because one thing's certain, the universe is still speaking, and the next ripple through space-time could rewrite everything we know. After all, every wave tells a story. What will the next one